Engineering a robot is the practice of building software that remains reliable as the underlying hardware and operational tasks grow in complexity. In a controlled environment, this arm can execute a pick-and-place routine with a simple script. The environment is static and the logic is straightforward. But when deployed across a fleet of mobile robots navigating a dynamic warehouse, simple scripts struggle to handle the influx of asynchronous data and edge cases. Because Python is highly flexible, it is easy for developers to treat ROS nodes as loose procedural glue code that links sensors to actuators without a formal structure. When code controls high-torque physical hardware, the software architecture must allow for regular maintenance and updates without introducing logic errors that lead to mechanical damage. To move from prototype to product, we will deconstruct a brittle ROS script and rebuild it using modular design, object-oriented programming, and rigorous testing. Moving from procedural scripting to structured software engineering provides the framework necessary to manage the complexity of a deployed robotic system. This monolithic script on the left is technically functional, but its lack of organization makes it difficult for a team to read and impossible to scale. We begin the refactoring process by enforcing PEP 8 standards. Using 4-space indentation and 79-character line limits ensures that the code remains readable for every developer on the project. In a monolith, hardware drivers, communication logic, and data processing are all tightly coupled in a single file, meaning a change in one area can have unintended effects on another. To prevent this, we break the script into separate logical modules, isolating the robot's mathematical models from the communication layer. By organizing these modules into standardized packages, developers can focus on individual components without needing to manage the entire system simultaneously. This modular structure ensures that an update to the path planning logic can be tested and deployed without interfering with the low-level motor drivers. Procedural ROS scripts often rely on global variables to track the robot's current position or sensor status. ROS operates on asynchronous message streams. If multiple topic callbacks attempt to update the same global variable at once, it leads to race conditions and inconsistent memory states. You can see the sensor inputs colliding at the top of this diagram. We resolve this through encapsulation, using Python classes to store data in protected internal slots. A class instance binds the robot's state and its methods together. This ensures that the node processes incoming message pulses in an organized, predictable manner. Because the logic is contained within a class, these methods can be reused across different nodes or projects, significantly reducing the amount of redundant code in your system. This object-oriented approach ensures that every command sent to an actuator is based on stable data that has been correctly scoped within the node. By localizing state within a class, we prevent asynchronous callbacks from overwriting shared data, providing a stable foundation for the robot's decision-making logic. Hard-coded configuration values, such as setting a speed limit directly in the source code, create another bottleneck in the architecture. If a robot needs to be slowed down for a specific environment, an engineer shouldn't have to modify the source code and recompile the application to change a single number. The ROS parameter server allows us to decouple this data. As shown here, the server can push new values to all nodes on the network instantly without stopping the execution. Instead of using a local variable, the node requests the required configuration from the parameter server when it initializes at runtime. This allows a team to manage a fleet by sharing a single configuration file across multiple different nodes. The codebase becomes adaptable. The same node can control different physical robots simply by pointing it to a different configuration file. Separating configuration from execution logic is what enables a single codebase to scale across different hardware platforms without manual intervention. In robotics, physical errors are a certainty. Sensors will eventually disconnect and hardware jams will occur. A script without error handling will simply crash when it encounters a hardware disconnect, leaving the robot in an unmanaged state. We implement specific try-except blocks to catch these anticipated failures, allowing the software to respond to an error rather than just failing. This allows for a cleanup phase, where the node can safely release hardware locks and bring the motors to a controlled stop before the process exits. To diagnose these failures, we use the ROS logging hierarchy. This funnel shows the levels of severity: debug, info, warn, error, and fatal. We use log info for general status, log warn for non-critical anomalies, and log error for faults that require an operator to intervene. This logging structure creates a record of the events leading up to a failure, providing the data needed to troubleshoot unpredictable hardware issues. Before code is deployed to drive a physical machine, it must be verified in a controlled environment. The Python unit test framework allows us to verify that our individual classes and functions perform correctly under a variety of inputs. Testing a ROS node can be difficult if the test requires the presence of an active robot or a specific sensor message. To solve this, we use mocks. As shown in this diagram, the controller class receives synthetic data from a mock interface rather than a physical sensor. Mocking isolates the software's logic, proving that the control algorithms work correctly even when the physical hardware is unavailable. Integrating these tests into the development cycle ensures that new code doesn't break existing functionality, separating software bugs from mechanical failures. A production-ready node must be architecturally sound, but it also needs to be sustainable for the people who maintain it. Clear docstrings and a comprehensive README file translate the technical assumptions of the code into a reference for the rest of the team. Version control systems like Git allow teams to manage changes through branches and code reviews, ensuring that only verified logic is merged into the main deployment. The resulting architecture is a clean, organized system where parameters are decoupled, state is encapsulated, and every action is logged and verified. We have moved from a brittle script to a scalable module by focusing on modularity, object-oriented design, and proactive error handling. This architectural approach ensures that a robot's behavior is predictable and maintainable throughout the entire lifecycle of the project.